Thank you for the reminder, Michelle. Oh, let's see, Jonathan. Some of the functions today's code challenge returned zero and they could have returned void. Uh, oh, what's an example? Point me at an example and I can check it out. There could be a reason or it could be an oversight. Let's see, why does printf percent s string print out a string when string is a pointer? Why wouldn't we need to loop through the elements of the character array? I love that question. Let's save it for when we talk about pointers. I'll I'll address it then. Let's see here. For some reason, val comes up as 101. Aha. All right. More pointers. I'll address that one with the pointers too. How about? You're right that the value val is 101, which is probably E. Um, but that is a great example. All right, Jonathan, I'll check that out and see if I can find one that does it. Often zero means no error of some sort. What do we start out with? Do we start with FizzBuzz? Well, main does. When you return zero from main, that actually returns a status back out to the operating system so that you can determine from outside the program if it completed or how it completed, if it failed or if it succeeded. And zero means success in that in that area. So definitely returning zero from main is going to be a frequent thing. But that return zero being success, that's that's a convention that only exists in main. In other functions, it may or may not mean success. Dig around a little more here. I like pointers Q. All right, let's talk about why. Why we're even doing this. Any ideas? It seems kind of arbitrary at first. Why learn C? Especially with the pain that pointers present. To feel the pain. I'm laughing, but in an indirect way, that's kind of true. Uh, if you can program in something in C, then probably you can program anything in just about any language. And I know you all can program things in C. It's just a matter of figuring it out. And that isn't for the sake of pain for its own reason. It's more like, hey, when you get to something later, some other programming language you haven't seen before, like you go to work one day and they're like, hey, guess what? We're switching to TypeScript for everything. You can be like, well, I figured C out, so I can probably figure TypeScript out without too much hassle. So several programming languages are made with C. In fact, usually when new programming languages get invented, people write the compilers in C or C++ to start. The lower level knowledge is definitely there. We haven't talked about computer architecture yet, but C is really only one step up above assembly language, which is the lowest level human readable language we write anything in. And writing stuff in pure assembly language is kind of a pain. So the inventors of C were like, I'm tired of writing these things in assembly language. Let's write a language that helps us. And so, being the first language built above assembly language in the Unix world, C was really only the thinnest layer on top of it. And if you know C and you know assembly language, as you're writing C code, you can kind of visualize the assembly language code. You can visualize the individual instructions that are probably occurring to make your program run, which is kind of neat. But we'll talk about more about assembly and stuff when we get to computer architecture. But for now, we'll just do stuff in C. Interestingly, C used to be considered a high-level language because, hey, it's way nicer than assembly language. But now people have taken the C language and they've said, okay, these are some of the difficulties we're having with this language. Wouldn't it be nicer if we had a language that was like C, except it also did this stuff? And this is kind of how all programming languages come about. They're like, oh, hey, I like that, but I could do one a little better. And of course, by better, I mean better in a particular context. There's no one language that's like the best language in all contexts. It's like saying in home construction, there's one tool that's the best tool in all contexts. It's just not true. Like, you know, you might have the best hammer in the world, but it's probably pretty bad at cutting wood in straight lines. The right tool for the job is the important part. And C is still sometimes the right tool for the job. Adrian, yeah, that is totally a good point. Better appreciation for runtime space complexity. With C, you have really fine-grained control over what the computer is actually doing. And you're like, hey, do exactly this, and the computer will do it. Even if it's a crash, you say, hey, do exactly this thing that causes a crash, and the computer will be like, ah, I crashed. That said, on a modern operating system like the ones we're all using, a crash is not that big of a deal. Like, you're not going to accidentally erase your hard drive or anything like that. You're not going to cause the computer to shut down. What you might see is something that says segmentation fault, and then the program will stop running, and you'll be back at your shell prompt. So even though we're all low level and stuff, it's totally safe. You don't have to worry about it with a modern operating system. So yeah, the idea is that we're going to learn something low level, trickier, and then other languages will be easier. You will feel achievement, yes. But there are lots of other reasons too. Uh, One of them is just learning programming languages in general it's good practice. So to be able to learn a new programming language, that's a skill, and we'll practice that skill by learning new programming languages. I can guarantee you over the course of your career, you're going to learn numerous new programming languages. There's simply no way around it, unless maybe you're a COBOL programmer, in which case, congratulations. But especially now with WebAssembly on the horizon, we're going to be getting to the point where people can write stuff in all kinds of languages. I've already written things in Go that I've compiled to WebAssembly and run on them in browser. And I know that C compiles to WebAssembly, Rust compiles to WebAssembly, tons of stuff compiles to WebAssembly. So it could very well be you're working at a place and they're like, hey, we have this app that we wrote for Windows and we want to take this number crunching stuff and we want to build it and build it to WebAssembly and then use it in our web app. So you'll definitely be learning new languages. So we have practice learning new languages, but there's another thing about C that I really like. And that is it's kind of on the opposite end of the spectrum from what you've been using. If you're in iOS and you're using Swift, you're using a language that's pretty highly evolved. A lot of steps have been taken between C and Swift. And Swift has a lot of features that are super modern and really useful. Python, really easy to use, really difficult to crash, not particularly fast, but totally gets the job done really well, and it's a super popular language. Then we have C, and it's kind of on the opposite end of the spectrum from all these things. It's really close to the metal, offers no memory protection, really, and a fair amount of hand holding. It has stuff in the standard library to say compare two strings of characters to tell you if they're the same, but those functions like that, they're really just like stepping through the characters one at a time and comparing them and then telling you what the answer is. So you get perspective with C that you don't get in other languages from sort of the opposite end of the playing field. And one of the ideas here that'll help you be a better developer is that you've worked on one end of the field. I'm going to call it the modern end as opposed to the easy end, but the modern end of the field. And then if you switch over to the C side, then you're going to get perspective from that. You'll be like, oh, hey, way over there, there's Python. And here I am over here, close to the metal. Pretty much everything else falls in between these two things. So you will have experienced development from both ends of the field. And hopefully that makes you more comfortable when you end up with a different program that's kind of in the middle. If you used a JavaScript where you're not declaring types explicitly, and the type is figured out dynamically at runtime, and then you switch to TypeScript where you have to be more explicit about what types of variables are, then you'll be like, oh, hey, I'm being more explicit about variable types, just like I was in C. I've seen this before. So you get that additional perspective. Plus, being able to program in C, C is a venerable old language with a tremendous history. If you see curly braces in your programming language, it's probably because curly braces were in C. The structure of for loops that you've seen in JavaScript is just directly from C. And so it's got this history, and you're participating in that history. And there's also a certain amount of, I could say it's a badge of honor to be able to program things in C. So you should be proud of it. That said, fasten your seatbelts because Kansas is going bye-bye. Yee! All right. It'll be fun. Any more thoughts on those lines before we start tearing into some pointer stuff? I'm gonna, unless you have specific questions about things like for loops and functions, I'm kind of just gonna let those go because they're gonna be very similar to the concepts you've already had. But feel free to ask questions. I'll encourage that. It's just that pointers are the hard thing. I haven't taken a Fortran class in a long time, but I did take one in college. Yeah, COBOL really popular in banking. When Y2K happens, tons of COBOL programmers were brought up out of retirement and paid huge salaries to go through the COBOL code that still exists, and you can still find job listings for COBOL. I don't even remember when it was invented, the late 50s by Grace Hopper. That's some staying power. But hey, even C was invented in like 1974 or something. All right, let's hack. Let me see here. Find myself some space to play in. Come on, Visual Studio Code. You can do it. If we have time, I'll have to show you some of that Rust code I've been writing. Do it, Tom. All right. I'm going to do a quick warm up here because some of you probably haven't done any of the C stuff yet. So we'll do a little bit of C code to demonstrate some basic concepts, and then we can start talking about what pointers are. If that sounds like a plan. Otherwise, the other bits of code that are there in the repo, those are the ones that kind of go through the steps of, hey, this is how C works. So the main part of the program always has a function signature that looks like this, or there's a variant where you get command line arguments out of it. But I'm just going to show a main like this. So this is the code that runs when you start the program up in the command line. Everything that's in main. And the quintessential starting program is, of course, hello world. And then main returns an integer. That's what this guy is saying here on the left of the function name. So if you're used to JavaScript, this is where you probably have the word function to declare a function. But in C, we have to be explicit about our types. And so we're saying main is a function that returns an integer. And so I'm going to return an integer. And I'm going to demonstrate returning something besides 0. I said 0 was success, but I'll return 2 just to demonstrate how it works. If I try to build this, it's going to give me a warning because it doesn't know what printf is. With C, you have to basically do what's equivalent to an import, equivalent-ish, I'm going to say. And it looks like this. So this is saying, hey, I want to use all the functionality that's declared inside standard.io.h, stdio.h. And I know from experience that printf is one of the pieces that appears in there. And the compiler will often tell you, like, hey, did you mean to include that? Actually, let's leave it off. I'll change it into a comment there. Now, in a lot of these programs that we've given you here, there's something called a make file, and you'll see in the instructions it says type things like make to, I was expecting that to give me an error. There we go. Took a sweet time. To run the program, but I don't have a make file. Basically, make file is like lists a bunch of commands to run to build a program. And so I'll just type one of the commands on the command line here. Normally, you guys would type make in this repo, but the command I'm going to use to build this program is called GCC. This is the compiler. So conceptually, what's happening here is I want to take this program I've written in C and I want to turn it into machine code instructions that the computer can run. And that takes a step called compilation. With languages like Python or JavaScript or like Node, you're used to typing in stuff and then running a program like python.exe or Node to cause your instructions to execute. And when that happens, we call that an interpreted language, that the program Python or the program Node is something that goes through your program and interprets the instructions and then does a thing depending on what the instruction is. And that's in contrast to what we're doing now. We're taking something written in C and we're going to turn it into actual machine code instructions that the CPU can execute directly. It doesn't need to be interpreted at that point. The CPU is just going to run the instructions that are made by the GCC compiler. I'm going to turn on some warnings so that I get maximum warnings from the compiler about my code. I'm going to tell it to output hello, and then I'm going to tell it to compile hello.c. Normally this line is inside the make file, so you don't have to type it, you just type make. But I'm going to do this, and it's going to say, what do we have here? Warning, implicitly declared library function printf with type this, blah, blah, blah. Note, include the header file standard.io.h, or explicitly provide a declaration for printf. So it's telling me like, hey, you're using printf, but you didn't include standard.io.h. So I'll change that to include it, and then we'll build it again. And hopefully this time it says, hey, nothing. No news is good news. So remember, this wasn't actually running it. This was just taking our C code and turning it into machine code instructions. And now if I look at my directory, I see I have a program here called hello. It's 8K long. And that is what I get to run my program. Good question, Jonathan. Yeah. So minus capital W means warnings, and minus capital W all means turn on all warnings. Now, one thing I've never understood is why the extra warnings that you get from W extra, why those aren't included in all warnings. But minus wall gets you some, and minus extra gets you the rest. There are actually even more warnings you can turn on, but this is sort of the limit where I don't want it to start complaining to me. But yeah. So now I've got this program hello. You might not know this, but in Unix you can use the file command to tell you what a file is. So I'm like, hey, what is hello.c? It tells me that it's ASCII text. It's a C program. Great. But I can also ask what hello is. It tells me that it's a Mach 64-bit executable for the x86-64. If we try to look at that program, it's going to look gnarly. Will VS Code even let me? No. Yeah, open it anyway. Blah. Bunch of unprintable characters. So this is wrapped up inside a certain file format, but inside here are a bunch of machine code instructions that the CPU can actually execute. So let's do it. There it is. Hello world. So great. And it ran very fast. It was actually sort of the fact that it had to output all this stuff to the screen. The CPU probably didn't have to work very hard for this. It wasn't like we were asking it to do math or something. We cannot run the C program directly, of course, because the computer doesn't speak C, and we don't have an interpreter at our disposal that reads it. So these are sort of the two main ways of getting your program to run. You can run it through an interpreter, like python.exe, or you can compile it into machine code and have the CPU run it directly. Interpreters tend to run more slowly. although that gap has been closed a fair amount in the last decade. But C is still pretty much the speed king because it compiles straight to machine instructions that the CPU executes as fast as it possibly can. On that note, there's nothing stopping you from having a compiler for JavaScript or a compiler for Python or an interpreter for C, for that matter. All these things exist. It's just that languages like C tend to be compiled, and so people refer to languages like C as compiled languages and languages like Python as interpreted languages. What's everybody think? So far, so good. Is everybody just waiting for the hammer to drop with pointers? On interpreter versus compiler? Yeah, a little bit more. I will also say, though, that when we get computer architecture, we're going to implement an interpreter ourselves. But yeah, the idea is so an interpreter is a piece of software itself. I can elaborate on that. So python.exe, that's a piece of software that was written in C, actually. And so what python.exe does is it reads a file, your Python code, and it actually takes those lines of Python, it converts them into an internal representation that it has. It's not machine code ever. And then it starts going through that representation it keeps internally. And it says, okay, if I've got an instruction that says store a value in a variable, then I'm going to look in my variable table. I'm going to put the variable there. I'm going to store the value in it. And then we're going to go to the next instruction. So there's a piece of software, the Python interpreter, that's doing this instruction by instruction for your Python code. And that's analogous to what the CPU is doing, except the CPU is doing it in hardware. So when we run a compiler like GCC, we turn that C program into individual instructions that the CPU can execute. And it does those in hardware, which makes it way faster. It's like there's one level of indirection is missing, right? With an interpreted language like Python, you have the CPU running python.exe, you have python.exe running your Python program. Whereas with C in a compiled language, you have the CPU running your program. That's it. Does that help? Why not go directly to the compiler? That's a great question. I mean, we can compile Python code. There's a program called PyPy that'll do it. So why not just compile straight to machine code and get the speed, right? Well, let me think. There are a couple of reasons off the top of my head that I can think of. One is that by having that additional layer in the middle, that gives you a chance to catch certain types of errors and handle them. So maybe you don't want the program to crash. Maybe you want the program to continue running. And so python.exe, while it's running your Python program, it can detect a crash and be like, oh, hey, you tried to divide by 0. You want to not do that? And then your program can keep running. You could be like, oh, yeah, I better catch that exception. I caught the exception. We'll keep on going. And then nothing bad will happen. Whereas in C, if you divide by 0, the program is just going to stop. And you'll be back out at the operating system. And there's not like, I'm going to say that. I don't know. Maybe Tom will correct me. There's a way to catch a divide by 0 in C. I can't remember off the top of my head. But if you do like a bad memory access or something, the program just crashes and that's it. So there's no chance for recovery. And that's kind of a bad thing if you have a program that you want to run for a long time and you don't want it to crash. For example, there's Ericsson is a company, they made phone systems for companies. So, like dial 9 to get out, that kind of phone system that works inside a company. The phone systems were run by software, and nobody wants a phone to crash. You don't want to pick up your phone and be like, I got nothing, because the software crashed, right? So Ericsson uses an interpreted language called Erlang that they made specifically for this. And crashes do happen because people write software and people make mistakes. But that system, that middle layer, that catches those things and makes sure that the program starts up again without the whole thing bombing. So that's one of the main benefits of that level of indirection. Another benefit is you don't have to compile. You don't have a compilation step. You just change your code and go run it. And of course, you pay for that because it runs a little more slowly. But for like large C++ projects or large Rust projects, compilation time is a big deal. My girlfriend works on software for stamps. I think it takes about 45 minutes to compile. And that's not even that long compared to some even larger builds in C++. Those are good questions. You guys will probably forget to compile a lot if you're not used to the compilation step. It happens to me all the time. If I've been programming in Python and I go back to C, I'll change my code, I'll try to run it, nothing changes. I'll be like, what? I changed all this code. Why did nothing change? I forgot to recompile it. So if you change a bunch of your code and nothing's happening, maybe you're forgetting to recompile. It happens to everybody. All right, let's hack on let's put some variables in here. I don't know what Swift is like. Swift, I'm sure, figures out what type you're talking about all the time. So in JavaScript and Swift and Python, you're just like, hey, I want a new variable like that. Let's go for it. And most modern languages are pretty good about it. Languages like Swift, I'm pretty sure, have type inference. So Swift would look at this and be like, oh, hey, A is an integer. We're good with that. If I try to build it, though, do you always have to specify type? It doesn't infer ever? Dang. Apologies to Swift. Some languages like Go and Rust, they'll look at a line like line 5 here and they'll be like, oh, it must be an integer, so we'll just make an integer. That's it. But here, C is complaining at me. Use of undeclared identifier A. You can't use it without telling it that A is a variable. In modern Python or modern JavaScript, you'd say like let or something like this, right? To declare that this variable exists. But let isn't a thing in C. You have to give it a type specifically. And this is an integer type, so I'm going to say int. Now I'm telling C that A is an integer and its value is 12. You could also do this on separate lines if you wanted, like that. But the important part is that you've declared A to be an integer type. And now the C language knows what you're talking about. And there we go. A little surprised I don't get an unused variable warning there, but whatever. And then we can also print this out using printf. Printf will look at this first string that you pass in, and it'll look for special characters like percent followed by anything. %d means print something out as a decimal number. So I'm going to go ahead and print out the value A as a decimal number there. So here we got %a. I'll build that. And it says hello world 12. Obviously, A gets inserted into this output wherever %d happens to be. So if I put %d in the middle there, A is going to come out in the middle. But printf is a function, and we're passing A to it. We can make our own functions. Void is the return type. Oh, sorry. I can zoom in a little bit more. How about that? Cool. So all functions return a type. Let's make one that returns a type. I'm going to call this add. I'll just call it add. An add function, and I'm going to give it two variables, int x and int y. So this is going to be a function that we're making. It's going to take two parameters, x and y, and I want to add them together and return the result. X plus t. So I'll do this. We'll do it like this. Get my results. All right, what's all this stuff? So I've made myself a new function. Functions in C have to be declared before you call them. So that's why I have add up at the top of the source code here. So we've got our definition of add, and then I call it later. If I were to define add down below like this, then we'd have a problem. The compiler wants to see it first before the call happens. All right, so this is really similar to something you might see in JavaScript. In fact, if I were to port this function to JavaScript right here on the spot, we would have something like this. And there we go. I know all you iOS folks aren't JavaScripty, but you get the gist of it. What's clearly missing here is the types. JavaScript is totally happy to dynamically at runtime figure out what types you pass in. And you could pass it a couple strings, or a string and an integer, or an integer and a floating point number, or a floating point number and a string. And as long as plus works on those types, and in JavaScript usually does, then this function will be fine. And it'll return whatever the result of this expression is. That'll be the type of the return. But C is unhappy unless you specifically say what types you use. So here we're saying we're going to pass in two arguments, x and y. They're both going to be integers. And then something's going to happen, and the return value from this function will be type integer. And so this should give us result 15. All right. Now, there are some type conversions that happen automatically between like integer types and floating point types. But for the most part, you have to explicitly do conversions if the types don't match up. So far, so good on this. A little warm up. If so, we can take a quick break and then come back and do pointers in earnest. Break. My cup is empty. All right. Those pointer questions earlier on, those are great questions. And I'm going to work up to addressing them by the end of the hour. So, all right, gang. If you have questions during the break, just go ahead and throw them in Slack, and I'll bring up the timer and Everybody grab some coffee. I'll catch you in 5. Oh man, I didn't have the rooster turned on. Boo. There we go. Got to do it right. What? Man, I love the rooster. Uh, all right. I'm going to begin talking about pointers by first talking about arrays very briefly, and then show how memory is kind of like that, and hopefully give some context for how pointers work. So I'm going to declare myself an array, and we'll call it array A. It's got 3 elements in it. I'm going to go ahead and, if I can type right, go ahead and initialize this to have 3 values in it, 10, 20, and 30. All right, so I've got an array here, and I can print out individual elements in this array. I can print out kind of a couple things, actually. I'll set a variable I to be 2, and I'm going to print out 2 things. I'm going to print out I and what's at I, if you don't ignore me. There we go. And what's at array I. Oh, I forgot to show you the return 2 thing. We'll do that later. So I'm printing out 2 things here. And this should work as expected. I sub 2 should be 30 because arrays are 0 based. So I'm printing out 2 things. I'm printing out the index into the array that we're using, and I'm printing out the value that's there. So this is probably second nature by now, because you all have used arrays, and you know that there are 2 things. There's the index, and there's the thing that's stored at that index. We have 2 pieces of data, right? You might be thinking, yeah, so I'm pointing this out because this is very similar to how computer memory works. Inside the computer, you have your RAM, and that's something that you see as a programmer as a big array of bytes. A byte is an 8-bit number. It's like a very small integer. It goes from 0 to 255. So computer memory you can think of as a big array like that. And because you can think of computer memory as a big array, there are 2 pieces of information associated with each element of that array. One of the pieces of information is the index into your memory array, and the other piece of information is what's stored there. Let that sink in for just a second. So you can think of memory as a big array, and we've got 2 pieces of information that we need. One is the index into memory, and 2 is the value that's stored there. Just like we had here with this array. So let's do something a little different here. I'm going to declare a variable of type unsigned char. I'll give it a value of 12. In C, a char type is an integer type. So this is like an int, except the biggest number it can show us is 255. Unsigned means they can only be positive. They can't be negative. So for this type, x can be any number between 0 and 255 inclusive. So I just assigned it 12. And I'm going to print this out as a %u for unsigned. Go ahead and print x out. Let's give that a shot. See if we're good. X is 12. Pretty straightforward. It's just like we were doing with int, except now we have a different type there. Still an integer type, but just a smaller one. Well, my question is, where in memory is this? the computer stores all your values in memory somewhere. There's a little asterisk there after that sentence, in case you're about to call me out on it. But for this purposes of this example, all these values are stored in memory somewhere. That means that not only is there a value, but there's another number associated with it. There's an index into the memory array. So we have the index into memory, and we have what's stored there. We know it's stored there. We know the number 12 is stored there. We don't know where it's stored, though. Let's see where it's stored. So if memory is a big array, we would expect the index to be an integer value in that array somewhere. And it turns out we can actually get that in C. Now, I've been using the word index to talk about what the name of that thing is. We've got the array of memory, and then we have the index into the array of memory. When we're talking about memory, there are other words for that index. So you can call it the index into the memory array, but a far more common word would be to call it the address of that variable. So whenever I say address of a thing, that's exactly the same as me saying the index number into memory where that thing is. So address of, same as the index number. There's another word that means the same thing as the index number. That is a pointer to the thing. So the address of this variable x that holds the number 12 is the same as the index into memory where this 12 is stored. And that is the same as a pointer to x. These words all mean the same thing. How's everybody feel? Is that good so far? We haven't talked about how to use pointers yet, but remember that memory is just a big array. A pointer is just an index into that memory array somewhere. Stony silence. In Unix, no news is good news. But rarely is no news good news on Slack. Thumbs up. All right, well, let's see if we can see what that number is. Now, normally in C, we don't actually care what the index number is exactly. It's some number. We don't normally care about it. But let's look, just because we can. You can print out the addresses of variables, or also known as pointers to variables, same thing, with %p. Now, I can't just do this because x is an integer, or rather it's an unsigned char, right? So %p wants a pointer, not an unsigned char. So what we need is a way to go from this variable to its address. We need to get its address in memory. And remember, an address is the same as the index into memory, the same as a pointer to the thing. It just turns out that there's an operator called the address of operator that will return a pointer to that thing. So here, x represents 12. Here, address of x represents a pointer to x. And then, because it's a pointer to x, we should be able to print it out with %p. And see what that is. Oops. Whoa. What is that thing? So I got a number 12 here because I said, first of all, print x. And then after the 12, we said print the address of x. Anybody recognize what this is? It's hexadecimal. So if you haven't messed around with hex, it's an integer numbering system. Well, it's a numbering system. Here is an integer number. It is simply base 16 instead of base 10. So this is some number, and I could actually, do I have pcalc installed on here? No. Quick, in JavaScript, what's the fastest way to convert something? Parseint? Is that right? Or is it lowercase p? There we go. So this number in hexadecimal is exactly the same as this number in decimal. So that is the index into memory where that variable is stored. That's clearly a big number, but I have a lot of memory. The number is probably larger than the actual amount of memory I have, but there's a whole thing about virtual memory that we're not going to get into. In any case, from my program standpoint, this is the index into memory that it thinks X is stored at. You're like, yeah, but what does that bias? What does that bias when we could just use X? Why do we even need to know its address? Well, we'll get there. All right. Remember that I said that everything in C has a type, and that the address of X, this is a pointer to X. Namely, it's a pointer to an unsigned char because X is an unsigned char. So I can actually declare a pointer up here. Oops. So this asterisk in this context is going to get confusing because the asterisk means different things in different contexts. Like sometimes it's part of a comment, sometimes it means multiply. But if you're declaring a new variable, when you're declaring the new variable, if you have the pointer next to the variable, the asterisk next to the variable name, it means that this is a pointer. So P is not an unsigned char, it is a pointer to an unsigned char, which means P is going to hold the index into memory of whatever X is. So at this point, I can change this to be like that. And that should also do exactly the same thing. Although we got a slightly different number on this run. So X was stored at a different place, but that's fine. I see typing. If the type of P is pointer, why do you have to specify unsigned char? You mean why is the unsigned char important as opposed to just being a plain old pointer? That is a good question. Let's see, do we want to talk about that now or in just a second? Because you're like, if a pointer is just an address in memory, it's just a number, shouldn't it always be the same, like an int, instead of a pointer to a specific type? It turns out that we're going to make use of it being a pointer to a specific type later on. So, in fact, we can do that. We can do that really shortly. Let me talk about one more thing here before we do that. We've gone kind of one direction here. We've taken a variable X and we've said, hey, I want to know what is the address of X. I want to know what that is. And so we were able to go from a variable to its address by using the address of operator. But I want to go the other way as well. I want to be able to go from an address back to the thing that's at that address. Think of that as like using brackets notation with your array. You already have the index I, but you want to know what's stored at I. And we can actually look that up too. We can look up what is stored at P. And what's stored there is an unsigned char. And I know that it's an unsigned char that's stored there because exactly related to Andrew's question, because P is of type unsigned char pointer. So we know it's an unsigned char that's stored there. So I'm going to print out an unsigned char. Let's say this is what's at P. But I can't just put P here because P is not an unsigned char. P is a pointer. I don't want to know what P is. I've already printed that out up here. I want to know the variable that's stored there. And so just like we went from the variable to a pointer by using address of, we can go the other way. We can go from a pointer to the variable that's stored there by using what's called a dereference. And that is an asterisk again. So this is one of those places where it gets confusing. If you're doing a variable declaration up here and you have an asterisk, it means you're declaring a pointer type variable. But if you're not doing a variable declaration, if you're just out in your code running somewhere, then what we're saying here is I want to dereference P. I want to see exactly what P is pointing at. I want to see what is at the address of P. I want to see what is stored in the memory array at index P, is what we're saying right here. And so if we give this guy a run, we see that X is 12. We see the address of P is this thing. And then we looked up the value that was at P, and we see that it's 12. So we can go from a variable to its address with ampersand. We can go back to the variable from its address with dereference. So ampersand and dereference are kind of opposites in a way. One turns a variable into a pointer, and the other turns the pointer back into the variable. And you can actually use this to great effect. Check this out. We'll say that X is this. Oops. I'm going to get rid of my pointer printout because I don't really care about that anymore. So we know what X is, and we know that the variable that's at P, it is X. So this prints 12 both times. Check this out, though. Oops. What happens when I do this? So we already know this line prints 12. We know this line also prints 12. This line is saying store into memory at the address P, store the value 15. So then the question is, what does this print out? X 15. It is the same as the first printf, but let's see the result. What happened? I compiled it. There was no output difference. I didn't mean to demonstrate this, but I forgot to save my source file. It's another thing that's going to happen repeatedly. You forget to save your source file, you recompile it, you run it, nothing changes. I forgot to save my source. All right, save my source file. Let's recompile it and run it. Now it says X is 15. So, holy cow. If I could draw this, we'll draw a chunk of memory here. I'm just going to put zeros everywhere except for where our X is. And so this is X right here in memory. This is just part of the memory array. And we had pointer P, which was the address of, oh, come on you, the address of X. So P is pointing to this thing. And then what we did in our code here, we printed out X, which was 12. And then we printed out the thing that P was pointing at because we dereferenced it. We printed out, we're like, hey, what's stored at the address where P is? P is pointing to the address that has 12 in it. So prints out 12 again. And then we're saying on this line, at the address that P is pointing at, I want to set that value to 15. And so it's like, sure, okay. P is pointing at this address right here. We'll set its value to 15. But hey, that's where X is. So X's value just got changed to 15 because we changed that pointer. So that's why X becomes 15 after we do this line. This is a sort of low-level control that you end up with in this language. So 12 is not the index. That's a good question. 12 isn't the index. 12 is the thing that's stored there. Remember, the index was that big old hex number. You can get into overflow exploits using pointers. So that's also a great question, Jonathan. Does it change anything or just return the value? And it depends on the context. So if I'm going to call it, we'll call it the read and write context here. So here we're reading the value. We want to print out what's there. So we print out that value. It's very similar to this line, line 14, where we read the value of X, right? We don't actually change it there. If we wanted to change the value of X, we'd have to put X on the left side of an equal sign, for example, and say like X is assigned 15, right? So similarly here, we're not doing any assignment. We're just reading the value. But here, dereference P is on the left side of an assignment. So we are changing its value. So when you're doing the dereference, whether or not the memory changes depends on whether you do an assignment into it or not, just like with a regular variable. Just like the printf X here doesn't actually change X, but the assignment to X up here, this does change X. Yeah, I would say it changes the pointer to the thing that's being pointed to, is kind of what it, if there's some change that you want to apply to it. The result of the dereference is the thing that's being pointed to, as opposed to the pointer itself, the pointer being the index. The pointer is the index, dereference the pointer is the thing stored at that index. I see typing. I see what you meant to type there because I can infer where the asterisks were. So yeah, it's a pointer always dereference. It can be anything as long as the asterisk precedes it. It's just a variable name, really. So whatever you can have, like pointer to whatever. You'll stop ignoring my key presses. Whatever. All right. So that's valid too. P is just a variable name. And pointer variables aren't really that special. They're special in that you can dereference them, but that's really it. It's just a name of a variable, and just like an integer stores an integer, a pointer stores a pointer. It's just a different type, that's all. So it's not actually that special. So at this point, a question might be, why are we going through all this trouble to make a pointer and change it by dereferencing. We could have just used x, right? I could have just said x equals 15 and be done with it. So admittedly, this is kind of contrived at this point. But let me show you the killer feature here, the killer application. So we saw in our adder before, or what I call add, we returned an integer, right? But let's say for some reason we can't return an integer. Maybe we're using the return value for something else. We need to return two things, for example. C can only return one thing of one type. But what if we wanted to return two different pieces of information? Maybe the return value is a success or failure indication, but we also need to get an additional piece of data out. Well, we could try to do something like this. Actually, I'm just going to call this add 10, and it's going to add 10 to a value, right? So before we would have had something like this. But now let's say for whatever reason, we can't return a value. So I'm going to change that to void. We can't return the value, so we can't return anything. We could do something like this, right? What does that get us? Let's print that out, %d, print out x. What's the output of this program going to be? Imagine you wrote this in JavaScript, or if you wrote this in Swift. Actually, I'm not sure how Swift works, so maybe Swift is different. But if you wrote this program in JavaScript, what would the output of the program be there? Because JavaScript and C work the same way. It's like it's either going to print 12 or 22, but which one and why? Any of you JavaScript people remember off the top of your head what this would do? Globally. Let me modify this ever so slightly. Just so I'm not using the same variable name. This one's not returning anything. I'll call it Y. So, oh, you're right. I did mean unsigned char. It doesn't actually. It doesn't quite matter. But here, let's switch to int. It's a good point, Michelle. So the void doesn't give us global scope. Add 10 is global itself, just because it's declared outside of anything else. So add 10 is global already. Question is, what's y? When I just ran this here in JavaScript, I made a function that adds 10 to y, and I passed in x to it. But when I printed x out again after the function, x was still 12. Why did that happen? Didn't I say right here I was going to take a parameter y and I added 10 to it? So why didn't x get 10 added to it after I ran this in JavaScript? Eh, closure. It's not the same memory address. So y is actually a local variable inside add 10. And sure, it got initialized to 12, and then we added 10 to 12 and we got 22, but then the function ended and y was gone, and that was it. We never changed the value that was at x. It all has to do with the scope. So I can print these things out. I can say like, hey, y is this, and we'll see what it is. And then we'll print it out again after we add 10 to it. And we can see that this will actually add to y. It says y is 12, just like we suspected, because we passed x, which is 12. We passed it in there. And then we added 10 to it, so y got to be 22. But x down here in main is still 12. And it's because we get a copy of x. Whenever you make a function call like that with a variable that's an integer, even in JavaScript, with simple types like integers, copies get made. So y becomes a copy of x, and now we have two things in memory. So first, I'm going to draw a very bare bones memory map here. So we have x, and that value is 12, and then we call the function, add 10, and then we get another variable, y, and its value is 12. Because we passed 12 in, y gets to be a copy of it. We print out 12, we add 10 to y, so it becomes 22. We print out 22, and then we return. And when we return, y is gone at that point because the function is over. But x is still 12. We never touched it. So my question now becomes, how can we make this work? Without returning anything, by using pointers, what could we do to make add 10 change the value in x? We do some dereferencing. Pass x's pointer. So what if we had a pointer to this? Oops. Just going to use a little arrow to represent the pointer. We'll call that pointer y. Now we can do something, right? If we have a pointer to the thing. So let's pass a pointer in there. So I have x here. How do I get a pointer to x? Dereference goes from a pointer back to the thing, but I want to go from the thing to the pointer. So yes, I want to do address of, because remember an address is the same as a pointer, same as the index in the memory. So to go from the thing to a pointer, we want to take the address of the thing. All right. If I try to build this now, let's see what happens. Warning, incompatible pointer to integer conversion. Passing int pointer to parameter of type int. Remove the ampersand, it says, which is actually not what we want to do. We could do that, but we're trying to go the other direction now. So why are we getting this error message? I've passed in, so I've got ampersand x, and I can say here the type of ampersand x is pointer, it's pointer to an integer. It's type int pointer. And when you call a function, the parameters you pass in have to be the same type as the parameters the function accepts. So here we've declared a function that accepts an integer y, but we're passing in an expression that's of type integer pointer. So yeah, we need to change this so that p is not declared as an integer, or sorry, y is not declared as an integer, but is declared as a pointer to an integer. So great. Let's do that. Well, it compiled. X is still 12, though. So what have we done? This is about to get interesting. So what we wanted to do here is we wanted to say the thing that y points at is equal to the thing that y points at plus 10. But that's not what we said here. We said y, the pointer, is equal to the pointer plus 10. Remember, y is just an index into memory. It's just an integer number. And so what we've done is, if there are more memory addresses out here, we've taken y from this one and we've bumped it out 10 to wherever that is. I'm not counting, but let's say that's 10. So we just moved the pointer. We're actually just pointing at some other arbitrary memory address now, which is where x was plus 10. You can do this. It's called pointer arithmetic. And we'll talk more about that later. But that's not what we wanted to do. We wanted to change the thing that y points at to the value of the thing that y points at plus 10. So what do I have to do to make this right? Dereference. The thing that y points at is equal to the value of the thing y points at plus 10. So now when we run this, we pass the address of x in, so y points to x, and then we say the thing that y points at, which is 12, plus 10, which is 22, we assign it back into the thing y points at, and we should end up with 22 for our thing. There we go. So this is a way for us to get information back from a function without using the return. In this case, again, it's kind of contrived. We could have returned the value, but maybe in certain other cases, you need to return values and you've already used the return value for something else, or if you need to return multiple values. We call this passing by reference because we're passing a pointer to the thing or a reference to the thing. All these words mean the same thing. Address, reference, pointer, index, it all means the same thing. But if in case you were wondering where dereference comes from, dereference is like depointering. Yeah, so this line, that's a good question because that line's the crux of it. Let me break apart this line into two different things. I'm going to declare another local variable here. I'm going to say a is dereference y plus 10. And then I'm going to say dereference y is assigned a. So this is exactly the same thing. I've just introduced a variable here temporarily in the middle. So what this first line is saying is, hey, the thing that y points at, let's compute the value of the thing that y points at, and then let's add 10 to it. So I have a new variable a here. We'll say a is right there in memory. So we take the thing that y points at, which is 12, and we add 10 to it. And then we store that result in a. And then on the second line, we're saying, hey, the thing that y points at, set that value equal to whatever a is. And so the thing that y points at is this address here. And we set that equal to whatever a is. So we'd set it equal to 22, like that. The thing is, David, after you get used to doing this, to messing with pointers, and after it clicks, and I'm not expecting it to click right away, you have to mess with it for a while before it does. But once it clicks, for people who've been doing C programming for a while, you do it without even thinking about it. It's like driving a manual transmission car. Like, you're like, oh, I have to dereference that, and And you can even have pointers to pointers. Like pointers just a variable. You could have the address of the pointer. You could have pointers to pointers to pointers if you wanted. It just takes it takes a while. It's like me with Rust trying to figure out borrowing and ownership rules. Like, what does any of this mean? It just takes a while before it sinks in. And you're like, okay, now I see how I can use this thing. With pointers, we've only got really two pieces of information. We've got the value of the pointer, that is the index into memory, and we've got the thing that's stored there. And we have these two operators, address of and dereference. Those two operators move from one of those things to the other thing. So we are able, if we have any variable, we're able to get a pointer to that variable with ampersand. If we have any pointer, we're able to get what that points at with an asterisk. So that gives us total coverage of everything that we need to do with pointers. Why don't we pass it with the address of? That's a good question, and I don't know the answer to that. And the best I'm going to have to punt at is that's the way the language designers decided to do it. So in C++, there is actually a thing called a reference that uses an ampersand in the function signature like that, but that's C++. So, oh yeah, we pronounce this bang G. The exclamation point is the bang character in Unix parlance. It's part of the command history. This means run the last command I ran that started with G. So it's a bash thing. You can also rerun the last command with if I can type. Hello, am I alive? No, that's weird. The keyboard works there. The keyboard does not work here. Strange. All right. You can rerun the last command with two exclamation points, or you can rerun the command like 3 commands ago, I think, like that. It's, yeah. Let's see. What advantage does the pointer provide? So there are a couple of advantages we haven't talked about yet, but one of them is if you have a large piece of data, like later on we'll get to structures, which are kind of like objects in other languages where you'll have a single type that encapsulates a bunch of types, a bunch of fields in it. So like in JavaScript, you'll have an object that has like 40, 50 fields or whatever, like a big object. You can have a large structure like that in C as well. Or you can have an array that's like 40 kilobytes or something. Now, as we saw with our first version of add10, when you call a function, a copy of that data gets passed to the function. And then we work with the copy. And that's okay if the copy is just an integer, you know, copy an int, no big deal. Computer does that without even thinking about it. But what if you have a structure that's like 50 kilobytes or something? It takes a little while to copy that much data. And so one of the advantages to pointers in C is that you can take a large structure, you can pass a pointer to that structure. Instead of passing a whole copy of the entire thing, you just pass a pointer. And pointers are small, they're like 8 bytes. So the computer can copy pointers in a big hurry as well. So that's one of the big advantages of it. The other big advantage, like I said, being able to return multiple things from a function. If you need multiple things to come back, the function only returns one thing in its return value. But if you need multiple things to come back, you can use pointers in this way. So those are a couple of the big advantages. A lot of libraries in C, if they use a structure for anything, they almost invariably pass a pointer to that structure to make it faster. Oh, what was I going to do next with this? Enough time for some pointer arithmetic and array stuff? Maybe. 7 minutes isn't that long. We already saw that little bit of pointer arithmetic where we added 10 to y and it pushed the pointer way out here. I'll cover this again tomorrow in more detail. But, oh, what I should do is go back and look at those questions and make sure we get those. That's what I need to do. What do we got? Okay, strings and pointers. Why does this print out a string when string is a pointer? Why wouldn't we need to loop through all the elements of the array? I like that one. Let's see. For some reason, this comes up as 101. Char makes, let's see. I get char from a function, return type char pointer. Is there something missing here, like a return statement? It seems like maybe you were returning val or something. Let's do the string one first, though. Yeah, return val. Oh, man. I don't know if I'm going to have time to get to that yet. We might have to, maybe I'll stay over a little bit and do it. Let's do the string one first. So, because strings are kind of interesting, they are pointers to characters. And so the question was, how does all that work? So anytime in C you see char pointer or something, you should be thinking that's a string probably. Not necessarily, but often it is. So what I have here is a pointer to a char, and I've got the string hello in memory. So in memory, the letters hello are stored. And they're stored as numbers. So like Marshall had pointed out, he's like 101 is probably an E. They're stored as ASCII values. There is, do I have this? Yes, I do. So let's see, octal, hexadecimal, decimal. Here we go. So every character that you can print has a value associated with it. So they can be stored in memory because memory stores numbers. And so you can store characters in memory. And so like lowercase e is right here, 101. Yeah, so I hold that thought. I can do signed and unsigned in a bit. So E is 101. So all that gets stored in memory. I'm just going to write them out as letters, though, so we can see what they are. And then we have char pointer S, which points to hello. But hello is clearly taking 5 bytes of memory here. And a pointer only points to 1 byte of memory. So it turns out if you have something in C that's multiple bytes, the pointer, the pointer points at the first thing. So let's do some stuff with this. Let's print out a character. Let's print out a single character with %C to print a character. And then I want to print out the thing that S points at. So I'm going to print dereference S because dereference takes a pointer, gives us the thing that it points at. And I'm also going to comment this out so that it'll build. Whoops. My last build command was not hello, apparently. No. There we go. So there it is. It's H. The thing that points at is the letter H. This kind of makes sense. It doesn't point. You can't point at more than one thing. His pointers only point at one memory address, just like the index into an array is only one number. You can't have an index into an array that's multiple numbers. You can definitely pull things out of an array that are multiple elements, but the index itself inside your array notation brackets is typically just a number. But we can also print this thing out as a string. So if I print it out as a string with %S, it expects S to be a pointer. But if I dereference S, it changes it from a pointer back to a char. It depointers it. So I'm just going to leave it as a pointer. So I can print out these two things. I can print out the thing that S points at, or I can print out the thing that S points at as a whole string. And then if we run that, we get H for the first character, and we get hello for the string. And that's fine, but let's write one of these. I'm going to write a function called printStir that takes a pointer to a character and prints it out. And we're going to use that instead of our printf. One thing I've left off here is that actually at the end of strings in C, like hello, it automatically put an extra character at the end. And that's called the null character. It's represented by \0. So this is a single character. It has the value of 0. So if I want to print this string out, what can we do? I know I can print a single character. There's actually a built-in function called putchar. We'll use that. So I can print, let's say all I can do is print single characters out here. There's my H. Okay. See it right at the front of my prompt. But what we want to do is we want to start printing these things out. I want to print H, and then I want to go to the next letter and print it, go to the next letter and print it, go to the next letter and print it. We saw earlier that you could do stuff like this. We could move the pointer by adding 1 to it, and that would move it to the next letter, right? Like that. So if I run that, it should print out an E. There's my E right before the prompt. So I have a way of moving the pointer around so I can print out individual characters. Turns out we can also do this. Dereference P plus 1. So add 1 to P and then dereference it. That'll do exactly the same thing. That'll give us our E. There's the E at the beginning. So we could do something like this. P plus 0. This is exactly the same as just dereference P because a number plus 0 is just a number, right? P plus 1 and so on. So we could do that. Hello. So again, we have P pointing to H, P plus 1 points at E, P plus 2 points at L, and so on. But that's irksome. What if I put out a different string in there? Seems like a good time for a loop. Let's do that. So I could do something like this. You can use a while loop or a for loop, a bunch of different ways to do this. I'm going to say, well, char pointer Q. I'll declare that, and I'll initialize it to be P, so that P and Q both point at the same place. And then I want to go until we get to this. So I want to go until the thing that Q points at is equal to a null character. So as long as P is not a null character, or sorry, as long as Q is not a null character, we want to keep going. Then I'm going to put a Q++ right there. And then I'm going to put char of the thing that Q points at. So what have I done? So Q starts at P. We check to see is Q null, the null character? No, it's not. So we print it out. We print an H. We print out, rather, the thing that Q is pointing at, which is H. And then we say Q++. Move Q to the next char. So at this point, Q comes over to here. And then we print out the thing it points at, E. And then we check and see if it's null, it's not, so we go to the next thing. Print the L, check and see if it's null, it's not, and we go to the next thing, and so on, until finally Q ends up down here. and we see that it is null, and we quit printing stuff out. So yeah, Sai, that is a perfect way to do it. This is not the shortest way, the way that I've done it here, but there are many ways. So let's give that a run. Hello, there it is. Doesn't have a new line at the end. Might as well add that to the string. We get our new line afterwards. So this is why when you pass a string to a function to get a string printed out, we pass in a pointer to that char, a pointer to the beginning of the string. And that allows us to do basically this. And this code we've written right here is what printf will do, something very similar. So everybody think. This is one of those things that rarely clicks at hour 0. It usually takes some programming messing with it before it gets to be basically muscle memory. So yeah, it's totally confusing. Like, oh man, when do I have to dereference? Especially when you got stuff like this. I'm declaring a new variable. So asterisk here means Q is a pointer. But here, I'm not declaring a new variable. I'm running code, which means look at whatever Q is pointing at and see if that value is null or not. So ampersand x, you can think of that as going from a variable to a pointer to that variable. So ampersand gets you to a pointer, and asterisk is the reverse. If you have a pointer to a variable, asterisk gets you back to that variable. Let me show you guys one more thing that may or may not clarify. If it doesn't clarify, then ignore it. Turns out that C also has array notation. Here, I'll comment this out so it's still there for reference. C has array notation, and it turns out that array notation is just syntactic sugar in C on top of pointer arithmetic. We saw earlier that we could print out the E by putting P+1 here, right? Because P points at the H, so P+1 must point at the E right here. So that's P+1. We saw that we can do that. It turns out that these two lines that I'm about to type are exactly equivalent in C. There is absolutely no difference between these two things. Oops, sorry, P+1, P4, P1. There we go. These two lines do exactly the same thing. The C-spec says they are exactly equivalent. Array notation in C is just a little wrapper around pointer arithmetic. So that might help because you're used to thinking of, oh, hey, I have an array, first element in the array. That's exactly the same as the pointer to the first thing after P by adding onto it. These are exactly the same. And likewise, dereference P is exactly the same as dereference P+0, because like I said, adding 0 to a thing does nothing. So these two lines are the same. And again, by that same rule, that's equivalent to this. So under the hood, arrays in C, they're just pointers. You can, of course, have pointers that point to things that aren't arrays. Just like we saw early on, we had a pointer to X. X wasn't an array. And so if you try to do something with that, like X sub 2 with array brackets, the thing would puke. Yes. Pointers are the one thing that makes this language hard. Just like with Rust, borrowing and lifetimes and ownership is what makes the language hard. The rest of it's just stuff that you already know. You just don't know, like, I'm used to console.log and now I have to use printf. But when you're learning a new language like that, a lot of times this is exactly what it is. You're like, what's the Python way of having a loop? I know I want to have a loop. Then you have to look that up. Oh, the example of the negative char. No, there's not one. I'm gonna drop you a link to a thing that where I talk about negative numbers. Turns out that there's a pattern of bits in memory, ones and zeros, and depending on how you choose to interpret that, the numbers can be negative or positive. So whenever you convert a number into a character with a ASCII value, ASCII always assumes that number is positive. And so you could have a bit pattern that sometimes represents negative numbers, but that same bit pattern also represents positive numbers for unsigned. So basically, it just uses the positive variant. Raise prototypes and slices. Let's see. Where is that? I swear I wrote something up. Oh, here we go. So this doesn't talk exactly about that, but it is a thing that is related. And so it talks in there about how the same bit patterns represent negative and positive numbers. So in short, a char can have a negative value, but if you go to print it out, it's going to use the positive version of that to print it out. That's also a great question. So it turns out in C, the specification leaves it open. So when you declare a char, the compiler may think it's unsigned or it may think it's signed, which is kind of weird. But by being explicit and saying this is unsigned, I'm like, I mean it, this is unsigned. It's just easier when we're talking about memory to start to imagine that the memory addresses hold values from 0 to 255 and that's it. When in fact they can also hold values between negative 128 and positive 127 if we made them signed. I don't want to work through the find char just yet. It's when you're learning stuff like this, it's really useful to hack on it. So take the stuff from that we've covered today and hack on it again and keep track in your mind, like, is this a pointer to a thing or is this the thing? That's sort of the big question to keep at the front of your head. The best learning happens when you're struggling with a thing. And if I just give you the answer, then there's some learning that happens there. But it's like when I was messing with Rust and the borrow checker, and I'm like, how does this work? And I had to hack on it for so long. Let me see here. And it's like, you can't do that. You can't do that. You can't do that. And I'm like, ah. But it was the fact that I wrestled with it for an hour that really helped clarify how it worked. And I had plenty of examples of people saying, like, this is what the answer should be. But those examples didn't help me until I worked through it. One last thing before we take off. I can show you some of the crazy Rust code that I've written here. Notice that Rust uses squirrely braces for blocking. Stole those from C. But here we've got some stuff, a function probably, and this function returns a monster type, and we've got probably an array here. So a lot of stuff looks familiar, but this is what I've been wrestling with. Other stuff doesn't look familiar. Ute, what does that mean? But hey, here's an ampersand. Turns out this means a reference in Rust. Another thing they kind of got from C. So it's all the same but different, but I had to wrestle hard with this to get it to the point where I got it. And there were some days where I would get into a corner and I'd be like, how do I undo this knot that I've tied? Like, I think I have to read this value. I have to write this value. The compiler won't let me. What do I have to do? Like, what's the pattern I have to know to make this happen? And doing a bunch of research and messing with it for a while, I finally figured out the pattern. And now when that thing happens to me in this particular language, I'm like, I know what to do. So anyway, hack on that stuff in the repo today. I think in the repo, did I give you the repo? It's in training kit, right? There should be an outline of what it is that you're supposed to do today in there. And if there's not, let me know. But it's basically working through the examples. There's a README that gives a suggested order for working through the examples. And it seems like, I don't know, if you get to malloc today, then you'll be totally on par. Oh man. Yep. Sorry, I'm eating into a brown bag. Totally go to that. It's a 2-day assignment, yes. All right, gang. I'll keep monitoring for questions, but yeah, if it's a good brown bag, go do the brown bag. And then keep hacking on it. It's not going to be easy. It's going to be confusing, but it will click eventually. I swear it. All right, keep the questions coming, gang. Thanks for sticking around. I'll catch you all later today.